Hi there. Welcome to the virtual presentation on analysis of fleet management and network design for on-demand urban air mobility operations. My name is Max Egorov, and I'm a research scientist at Airbus UTM. This work is a collaboration between Airbus UTM and my colleagues Sheng Li and Michael Kokendorfer at the Stanford Intelligence Systems Laboratory. I'll be covering the first half of this presentation, where I'll provide background on the topic, our motivation for embarking on this research endeavor, and details on the approach we took. Sheng Li will cover the second half, in which he'll discuss the modeling and simulation that were enablers of this work, the results, and the conclusion. Let's get started. I want to start by answering the question, what is urban air mobility, or UAM? Well, it's more than just a vehicle. It's a complex and interconnected system of systems that has the goal of providing air transportation in our cities. Here we highlight some of the many systems that make up UAM. The ground infrastructure, which provides places for vehicles to land, take off, and recharge or refuel. The aircraft, which carry passengers through urban skies. The supporting services, which help maintain a high level of vehicle reliability and safety. The traffic management system, responsible for coordinating and enforcing safe airspace usage. And the operations center, responsible for efficient day-to-day operations. We refer to this complex system of systems as the UAM ecosystem. From an engineering perspective, an ecosystem-level view of UAM complicates design significantly. Consider this example. Say we have a simple network of vertiports that are connected by a set of routes UAM vehicles can fly. We have a UAM operation that is ready for takeoff. We may have an operations center that manages what the operations in the network do, and maybe even other vehicles in transit. Now, at the time of our operation, which design choices become more important for things to run safely and efficiently? Is it how the underlying vertiport infrastructure was designed, its location, recharge capability, and capacity? Or is it the fleet management policy that the ops center is following? Or is it some other design choice driving the performance of the system at this stage? Well, consider this. Both the vertiport infrastructure and the fleet management policy are important for a performant UAM ecosystem. But we must note that designing and building the vertiport infrastructure takes a tremendous amount of time, likely on the order of years. While the fleet management policy, on the other hand, can be changed just prior to takeoff. This is exactly the problem of UAM ecosystem design. We're analyzing and trying to make choices about interconnected systems and design variables that were built on different timescales, interacting with one another. In fact, the performance of such a complex ecosystem can be very difficult to evaluate before it becomes operational. However, in the age of UAM, we have computational tools to answer some of these complex questions. Simulation can help, and we leverage it extensively in this work. To help us navigate the complex UAM design space, we introduce a simple formalism that helps group different design choices or design variables together. We define three categories of variables that are based on the time horizon between the operational readiness of the ecosystem and when the design decision needs to be made. We call the first category long-term strategic, or simply long-term. The design variables that fall into this category are typically related to infrastructure and UAM network design, vertiport placement, and vertiport constraints. The design variables in this category may need to be chosen years in advance of a UAM operation. We call the second category short-term strategic, or simply medium-term. The variables in this category are related to UAM route design, vehicle capabilities, and fleet size. Medium-term design variables may need to be chosen months to years in advance. The last category refers to tactical or short-term design variables. It encompasses choices related to fleet management or traffic management and inter-operator coordination. Variables in this category can be chosen hours or even minutes prior to the start of an operation. It is the choice of all the design variables together that ultimately guide how the UAM ecosystem performs. In this paper, we aim to analyze how the design choices in each of these categories are related to one another, and which are the most critical to a performance system. Building on this, we highlight two primary objectives for this work. The first is to evaluate the impact of UAM design variables on performance of the UAM ecosystem. Specifically, we use simulation to analyze how design variables from the long-term strategic, short-term strategic, and tactical categories each impact performance metrics like throughput, delay, and utilization. The second objective is to provide ecosystem design guidelines and recommendations. We do this in two ways. The first is through a structured framework that relates design variables to one another, either through the long, medium, and short-term categories described earlier, or by characterizing simple relationships between design variables as a means of estimating bounds on how they impact system performance. The second way in which we provide guidelines is by leveraging numerical optimization techniques in tandem with simulation to extract design variable sensitivities. This allows us to identify robustness in our design choices and to ultimately extract critical information about regions in design space that are more sensitive or more robust to change. I'd like to discuss the exact UAM design variables we analyze in this work. We consider a design variable from each of the long-term, medium-term, and short-term categories. We note that a number of critical UAM design variables are not covered here, and we leave their analysis for future work. In the long-term strategic category, we analyze vertiport capacity. Specifically, we look at the capacity of a vertiport to accommodate an idling vehicle and to provide necessary maintenance on a flight-by-flight basis, such as battery recharging or swapping. We capture this design variable by a quantity we call normalized vertiport capacity. This value is represented by a ratio of the total vertiport capacity in the ecosystem to the total fleet size. In the short-term strategic category, we consider the fleet size serving the ecosystem. This is simply the total number of available UAM vehicles that can be utilized during operation. In the tactical category, we look at the fleet management policy used by an operator. Specifically, we consider an on-demand policy which responds to operation requests in real time, an on-demand policy with rebalancing, which additionally rebalances the fleet geographically in order to better accommodate demand. And lastly, we consider a fixed schedule policy, which uses a pre-computed optimized schedule based on anticipated demand profiles. Each of the policies is implemented algorithmically in this work. We discuss the details of each policy in our paper, but leave those out here in the interest of time. We should mention that we consider only a single operator in our analysis, but it's likely that the UAM ecosystem will comprise of many operators. A framework for coordination, resource allocation, deconfliction, and negotiation will be needed between operators to ensure safe and efficient airspace access. The system responsible for this may resemble what is known as UAS traffic management, but we leave the analysis of such a system for future work. Before diving into our experiments, I want to briefly touch on the approach we took in our analyses. Specifically, I want to point out two critical concepts. The first is our simplified surrogate model that estimates demand for a given vertiport and UAM network configuration along with the fleet size serving it. We use the vertiport capacity variable and the UAM network configuration to estimate a rough bound on end-to-end time for an operation. This time spans from operation start to being ready to fly again. We refer to it as T operation. We combine this variable with the fleet size F to come up with a maximum demand bound the fleet and vertiport network design can accommodate, assuming the fleet is being fully utilized with absolutely no disruptions or wasted time. This bound is denoted by d hat max in our expressions. While it provides only an upper bound, we leverage it in our design and analysis frequently. This bound can also be considered as a rough estimate of the capacity of a UAM network and fleet in the ecosystem, beyond which the system will have exponential drops in performance. An effective fleet management policy should see maximum operational throughput approach this bound. The second concept is related to ecosystem optimization. In our analysis, we optimize a cost function J, which is typically a weighted sum of the performance metrics in our ecosystem, such as delay, throughput, and utilization, with respect to three design variables we consider in this work: vertiport capacity Cn, fleet size F, and fleet management policy pi. Our cost also depends on a number of other properties of the UAM ecosystem, which we consider parameters rather than variables here, such as the vertiport configuration V, the network configuration N, and the demand D. By evaluating this cost function through simulation, we can determine which regions in the design space of our three variables impact ecosystem performance the most. In the next part of the presentation, Sheng will cover our approach to simulation, the results of our work, and the conclusion.
Hello everyone, my name is Shane. I'm going to cover simulation modeling, results, and conclusion. We use an event-driven simulator in this work. This simulator models high-level operational states a vehicle might find itself in under a nominal operational profile such as takeoff, landing, and maintenance. Our simulation doesn't consider the physics model at every time step. Instead, it abstracts the dynamics of each process into time durations, allowing us to efficiently evaluate the impact of UAM ecosystem design variables. We represent each entity using a probabilistic model known as a Markov process, where each transition between states and the time duration spanning each state are governed by a probabilistic model. Starting from the ready state, an aircraft idles for delta-t idling until receiving an operation request. An operation request is generated by sampling a random distribution, and it passed into the model through an operation center. Then the aircraft enters the departure state, holding for delta-t ground holding until a departure slot is available. Then it takes off and flies towards the destination vertiport. Upon arrival at destination, the aircraft is held airborne for delta-t air holding until a landing space and an approach fix are available, at which point it lands. After spending delta-t turnaround for turnaround procedures, the aircraft will be in the ready state again. Proper demand modeling is a critical component for evaluating the UAM ecosystem. We model demand by generating requests using a Poisson process. Our baseline model is independent of time. While this model is not realistic, it's useful for examining the steady-state performance of a UAM ecosystem. A time series of requests generated by this model is shown in the figure on the left. A more realistic model uses a time-dependent demand rate. Using a Gaussian mixture model, we can emulate peaks and lows in demand for UAM operations, as shown in the center figure. By shifting the center and height of peaks in a Gaussian mixture, we can create geographically imbalanced demand rates for different vertiports that emulate rush hours to and from city centers. The figure on the right shows an example of such a scenario, where the demand from a specific vertiport is shown in different colors. This video shows how our simulator works. Here we have a 3 vertiport UAM network, with a fleet size of 30 and a normalized vertiport capacity of 1.4. The demand rate is 30 operates per hour and is geographically uniform. Traversing between landing and takeoff fixes is configured to take about 1 minute, while the turnaround time is on the order of 10 minutes and is modeled using a normal distribution. The operations follow an on-demand operation policy with fleet rebalancing. Our first analysis examines a UAM network in San Francisco Bay Area. We assume an aircraft cruise speed of 140 km per hour and the time durations mentioned in the previous slides. We use a fleet size of 36 and analyze how the other two design variables, vertiport capacity and fleet management policy, impact delays and time utilization as we vary demand rates. These figures show the demand delay, or the delay an operator might experience between their intended takeoff time and the actual takeoff time. We compare the 3 fleet management policies introduced earlier: fixed schedule, on-demand, and on-demand with rebalancing. We first note that increasing normalized vertiport capacity has a minimal impact on delays for all 3 fleet management policy considered. Second, the on-demand fleet management policy with rebalancing significantly outperforms the other 2 in the shown configurations. Third, we observe an increase in delays at lower demand rates for fixed schedule policies. This occurs due to the sparse nature of operation requests at low rate. This is similar to how one may experience long wait times when waiting for a bus in a rural area, where buses run at low frequencies because of the low demand. Note the location of our estimated maximum demand bound in the figure, which is 67.5 operations per hour, according to the ecosystem configuration. We see delays for all three management policies increase rapidly after demand passes this value. Next, we look at time utilization for the three fleet management policies we are analyzing under various demand rates. The bar plots here show what state the vehicle is in between consecutive operations. Specifically, we look at the amount of time a vehicle spends en route, air holding, idling, in a turnaround state, or flying empty due to rebalancing or being scheduled but flying no passengers. We observe that the on-demand fleet management policy without rebalancing sees significantly more air holding time when the normalized vertiport capacity is 1. Either increasing the vertiport capacity or introducing rebalancing into policy substantially decreases the air holding time. Both approaches lead to a more distributed fleet and thus more free space and congested vertiports, helping eliminate the air holding problem. Fleet rebalancing is essentially actively creating additional traffic flow to compensate for the unevenness of fleet distribution across the network inflicted by stochastic demands. Notice that when demand rate exceeds estimated maximum capacity, which is 67.5 operations per hour, idling time trends towards 0. This implies that the UAM fleet is being fully used to carry passengers and prepare for next operation. This explains the rapid increase in demand delay shown in the previous slide, when the demand rate exceeds our estimated maximum demand bound. These figures show the throughput analysis for the uniform demand model. Throughput is defined as the average hourly rate of completed operations in the UAM ecosystem. The red dashed line marking the unimpeded throughput indicates a throughput rate that is equal to the demand rate. These figures also show our per hour rates for operations completed within a specific delay window ranging from 1 minute to 2 hours. We observe that normalized vertiport capacity has little impact on net average delay and the overall throughput of the system. Additionally, the average throughput begins to flatten beyond around 75 operations requests per hour for all of these fleet management policies, which coincides with the estimated feasible demand capacity bound. However, the delay performance differs drastically between fleet management policies. Specifically, we observe increasing system-wide delays as the management policy changes from rebalancing to non-rebalancing to scheduled operation. Results of the Gaussian mixture demand model are similar to the results of the uniform demand model. They can be found in our paper. We now examine the results of our optimization analysis, which uses the performance cost J introduced earlier. Recall that J is a weighted sum of the performance metrics of our ecosystem. Please refer to our paper for the exact details on how J is formulated. In this analysis, we optimized the cost with respect to a short-term strategic design variable, which is the fleet size F, and a long-term strategic variable, which is the normalized vertiport capacity V. The tactical design variable, fleet management policy pi, is fixed to on-demand operation with rebalancing, since Through analysis, we have already found that this is the best performing strategy for stochastic demands. We also fixed the UAM network configuration, aircraft speed, turnaround time, landing and takeoff time. We use a Gaussian mixture demand model with peak hours at 8 a.m. and 4 p.m. and a peak rate of 30 operations per hour. The results of UAM ecosystem design optimization are shown in these figures, where Figure A shows a 3D surface plot for the cost, and Figure B shows a 2D heat map. The optimal design point is a fleet size of 36 and a normalized vertiport capacity of 2. We can see from the landscape of the cost function that it is high under small fleet size and low vertiport capacity, and it is more sensitive to small fleet sizes. There is a relatively flat zone for cost as fleet size and vertiport capacity exceeds sensible threshold levels. This relatively flat landscape in the cost function indicates that once sensible values have been chosen for design variables like vertiport capacity and fleet size, the performance of the UAM ecosystem is mostly impacted by fleet management policy, as pointed out in previous slides. We further explore the sensitivities of the cost to each design variable. These figures analyze the sensitivity of each variable at the optimal point. We vary one of the design variables, treating it as a fixed value, and see how the optimal cost and the other design variable will change if we want to achieve a relatively optimal cost under the suboptimal condition. The results of sensitivity analysis shed light on how designers of UAM ecosystem can evaluate the risk of a potential wrong decision about a design variable. A design variable that leads to less sensitivity in the cost may need minimal or even non-adjustment to move the performance of the ecosystem closer to the optimal point. Figure A shows the sensitivity of the optimal cost and vertiport capacity with respect to the fleet size. Optimal cost is shown not sensitive to changes of fleet size around its optimal value, and vertiport capacity has changed within plus and minus 0.5 to achieve the suboptimal cost. The relatively large fluctuation in the vertiport capacity does not lead to significant fluctuation in the cost. Figure B shows the sensitivity of the optimal cost and fleet size with respect to vertiport capacity. The sensitivities to changes in the fleet size and vertiport capacity design variables are again minimal. Both results imply that vertiport capacity and the fleet size are low-risk variables in the UAM ecosystem design process for the configurations tested in this work. Once a sensible value for these variables has been picked, the ecosystem is likely to be high-performing even if the capacity value is not the optimal for the configuration in question. We again note that the performance of the ecosystem is tightly coupled to the fleet management policy, and the results shown here are valid only when a proper fleet management balancing and when proper fleet rebalancing and management policies are applied. As a conclusion, in this work, we examined the performance of a UAM ecosystem operating under a variety of design choices using simulation. We categorized design variables into strategic long-term, strategic short-term, and tactical time horizons. We quantified the impact of various design choices on UAM ecosystem by evaluating the performance metrics such as throughput and delay time. We show that it is possible to design a high-performing UAM ecosystem even when the UAM network and the fleet serving it have not been optimized for the demand profile that emerges in that ecosystem. Instead, an effective fleet management policy can play a significant role in how the system performs. For future work, we would like to explore off-nominal operation and system with disturbances. We want to investigate a wider range of design variables, including geographical locations of vertiports. And last but not the least, we want to see the impacts of multiple UAM operators coexisting in a local region.